Hi, NA Physics. Let's talk about diffraction. But before we do, why did the man want to buy 9 tennis rackets? I'll tell you at the end of the video. So we're talking diffraction today, and diffraction is when waves will bend around obstacles. It's one of those 4 wave behaviors that we talked about in the last couple of videos. Everybody's familiar with this, especially with sound, because you know that you don't necessarily have to be in a straight shot from something to hear it. And not even just that, but there can be an obstacle between you and it, and you can still hear it anyway. So sound is able to get around obstacles, and we want to see why. So here we've got a person in a window on the other side of a window, and the sound source is inside of this little room source here. And if it weren't for diffraction, the sound would just travel straight out, and only a person straight in front of the window would be able to hear it. Versus, we know that sound actually behaves more like this, and it will spread out. I want to be able to let you calculate this angle here today, and you'll be able to do that whenever you're done with the video. You'll also be able to know, sometimes you get a lot of diffraction, this angle's large, and sometimes it's rather small, and you should be able to know, even without calculating, whether it's going to be large or small. That is, whether you get a lot of diffraction or a little bit of diffraction. So you might not have thought, but you get diffraction around obstacles, and you get it around windows or slits or openings. So you can see on the left, we have a window or an opening. A lot of times, particularly with light, we call this a slit. And so the waves are coming in here. These are on the left here. These are the incident waves coming in, and then they're encountering the slit. And so they are starting to spread out. And so you can see that maybe by rights there shouldn't be a wave over here because it's covered up by the obstacle, but wave is getting back there. That's diffraction. Now you can also see that same thing whenever you look at an obstacle like this. A real classic thing is to take laser light and shine it on a human hair and look at the diffraction around it, and from that you can actually calculate how thick the human hair is, something we'll talk about later on in the year. Here we've got this obstacle, and so there should be a shadow region behind the obstacle. And you can see that there is a shadow region, but that shadow region doesn't just continue on forever. The waves are filling in that area somewhat back there. And eventually, it's as if the obstacle wasn't even there. So we're getting diffraction around an obstacle. We're getting diffraction around an opening. And what I'm going to show you here today mathematically is going to work the same way for each one of these. I'll let you calculate this angle right here. I'll let you calculate this angle right here. In real life, you can see diffraction very well when you're looking down on the ocean. You can see all of these pictures are similar in that there are obstacles, little barrier islands or something like this, and the waves are able to get around those barriers. I think this one right here is especially neat. It's showing that the waves are coming through these slits. It looks almost exactly like that picture that I just showed, but you can see that same thing's happening here. Particularly, look how little this is, but waves are getting back in here. And look at this teeny tiny opening in the rocks, and waves are making their way around. So you can see diffraction's a real thing. Now, how much diffraction you get depends on 2 things: the size of the wavelength and the size of the opening or the size of the obstacle. So you can see over on the left picture, that's a picture of diffraction. Yeah, waves are becoming bigger than the opening, but not that much bigger. It's not a great example. Over here on the right, it's a way nicer example. You see how waves are spreading out, and by the time you get over here, 10 wavelengths back, it's way bigger than the opening was. So we would say that on the right is a way nicer example of diffraction. On the left, not as great of an example. It's there, but it's not that great. Well, the quantity that shows you how much diffraction to expect is something that I have started to call over the years the diffraction fraction. Now, that's not a standardized thing. You're not going to see that in a book. I don't know why people don't call it that. It rhymes, it's cute, and it really does show you how well the diffraction happens. And so it's this ratio, it's this fraction, and it's the wavelength over the size of the opening or the size of the obstacle. So going back to our 2 examples here, the D would be this distance right here, D. capital D, lowercase d, whatever you like. There I've got a real big one, and here a way smaller one. Versus the wavelength, well, the wavelength is the same in both cases. So on the left, you have a wavelength divided by a d in the denominator like this, and you're getting a pretty small fraction. Versus over here, same wavelength, but now over top of this little small denominator, and now I'm going to get a way bigger fraction. And look, this is a nicer picture of diffraction, and that's a lesser picture of diffraction. So now, it turns out that that is the thing that lets you calculate, because the sine of theta, the sine of that angle of diffraction, is equal to that diffraction fraction. And so we set it up just like that. Sine of theta is equal to wavelength over the distance of the slit. Now, when we get to light, because the wavelength is so small compared to most physical things, we don't just get one spot of area of wave. We actually get many spots of wave. And so for light, we're going to put in an integer in there. 0, 1, 2, 3, and so forth. More on that in the upcoming weeks. For now, we'll forget about the m, but I couldn't resist the chance to put that in there. Okay, and so now on this example, we have an opening, a doorway, and there are sounds going through the doorway. Now you can see that the doorway is 77 centimeters wide, so a D of 77 centimeters, and you're going to see that we're going to want this to be in SI units because we want numerator denominator on that diffraction fraction to cancel out. And so I'm going to make that 0.77 meters. And we have a speed of sound here is 343. They're saying find the diffraction angle when the frequency of the sound is 5,000 hertz and 500 hertz. Now, think about this conceptually first. Which one of those two would you expect to show more diffraction with the same size opening? Pause the video. So, me too. I would say since this frequency is large and this frequency is smaller, well then that means that this wavelength is large and this wavelength is smaller. Why? Because both of those have to multiply to give you the same wave speed. Now the one with the bigger wavelength will have a bigger numerator in the diffraction fraction, and so I'm expecting that diffraction fraction to come out to be larger because it's got the same denominator. Let's see if that's the case. So we know from the last one, sine of theta is equal to diffraction fraction, wavelength over the distance. I want the angle, so I'm going to make this theta equals arc sine. Now, I could go ahead and calculate the wavelength if I wanted, but couldn't I also say since wave speed is wavelength times frequency, for wavelength, couldn't I put in wave speed over frequency times 1 over d, just like that? And so you'll see if you go ahead and put in for part A, if you put in a 343 in the numerator, a 5,000 hertz in the denominator, and a 77 centimeters, aka 0.77 meters in the denominator, you're going to end up getting an angle of 5.1 degrees. Versus if you only put 500 hertz in that denominator, well, we're going to get 10 times bigger fraction, and yeah, it's not 10 times as much angle, but it turns out it's a lot bigger. It's actually more than 10 times as much, 63 degrees. So we were right. The bigger frequency had the smaller wavelength, and the wave diffracted less. And so 5 degrees, heck, that's only, I probably still made it too big. So 5 degrees would be this, and so those waves would be spreading out like that in part A. Versus in part B, 63 degrees, it's probably even more than the picture shows. So for part B, it's going to be this biggie right there. Notice something too, the 5.1, the 63, that's from center. So those are technically called half angles. So if you went all the way from there to there, it would be 2 5.1s or 10.2. And if you went all the way from here to here, it would be 126 degrees. And last but not least, why did the man buy 9 tennis rackets? Tennis too many.